Okay, so remember from the previous video that when we're trying to solve a congruence, one thing you can do is to divide both sides of a congruence by the same number, and depending on whether or not it is relatively prime with a modulus, you can just divide by that number, in this case 2, right? Or you might have to divide by the GCD. Now, there will come some times where you can't divide by the same number on both sides, and that's what these multiplicative inverses are for. Right, so take this example, for instance. 3x is congruent to 5 modulo 7. Right, so I can't really divide by 3 here, or divide by 5, right? Doesn't really make sense to have fractions in the congruence. And so, what else can we do? Well, it turns out that if you know what to multiply to both sides of the equation, so that you do get x is congruent to a number mod 7, then you would have solved the congruence as well. Right? And so what do we do in this case? Okay, we can try a bunch of numbers. If you multiply by 2 on both sides, you'll get 6x is congruent to 10. Okay, doesn't really help there. Or it might, right? But it might take a bit more work. If you multiply by 3, it's 9x is congruent to 15. 9 is the same as 2 modulo 7, and 15 is the same as 1. So getting there, you can probably already see from that step there what the solution is. But let's keep going until we actually get just an x here on the left side. So you can multiply by 4. That gives you 12 and 20. So 12 modulo 7 is also 5. It's not what we want. Multiply by 5. Okay, let's multiply by 5. We get 15 on the left, 25 on the right. Reducing this modulo 7, this becomes just x on the left, right? Because 15 is congruent to 1 mod 7. And on the right you have 4. And just like that, we've solved the congruence, right? It's the congruence class of 4. All those integers satisfy this congruence. And really what we just did there was to multiply both sides of the congruence by the inverse of 3. And not just any inverse, but the inverse of 3 modulo 7. And again, the idea there is actually quite similar to the equation scenario. If you have 3x equals 5, well, instead of dividing by 3, you can also think of it as multiplying both sides by 1/3, right? And 1/3 is called the multiplicative inverse of 3 because when you multiply them together, well, you just get 1 on the left. And on the right, it's 5/3. And that's your answer. All right, so this is for equations. We will say in this congruence that 5 is an inverse of 3 modulo 7 for the same reason. Because when you multiply 5 and 3, you get 15, and it's congruent to 1 mod 7. Right? So it has the same effect as multiplying by this reciprocal on the left here for real numbers. Right? Just that multiplying this integer to 3 gives you a 1 under this congruence relation. And so we can define a multiplicative inverse of a number a modulo m in general to be just any number b, such that when you multiply a and b, you get something congruent to 1 modulo m. And so really we have a question here, and it's how do we find these inverses in order to use them? Right? In the previous example, it was easy enough. It was modulo 7, right? So you only have 7 choices, 0 to 6, as the possible integers that when you multiply to 3, you'll look for one of them, such that it gives you 1 as the product. Right? In fact, how do we even know whether a natural number A has a multiplicative inverse modulo a specific m? And this condition here actually gives you what you need. It turns out that if A and m are relatively prime, then A has a multiplicative inverse modulo m. And that's actually an if and only if statement. It has a multiplicative inverse modulo m if A and m are relatively prime. Okay, so now the question is, again, how do we look for a multiplicative inverse in order to solve congruences this way? Okay, so for instance, find an inverse of 11 modulo 25. Okay, this question is the same as asking, find an integer b so that 11b is congruent to 1 modulo 25. And if you have enough time, right, you can plug in b equals 0, b equals 1, b equals 2, and so on until you get to, a product of 1. And you just have, 25 numbers to check there. But, you can do it that way. But let's do it systematically here. And first of all, I'm going to say that we know that an inverse exists because their GCD is 1, right? 11 is a prime number, and 25 is 5 squared. So what I'm actually going to do here is to take this congruence that defines what it means to be an inverse and then rewrite it as the following statement, right? That's the same thing as saying 25 divides 11b minus 1, right? From the definition of congruence. This, in turn, by the definition of divisibility, tells us that 11b minus 1 can be written as 25k for some integer k. Okay, so how does this help us here? I can actually rewrite this statement as, let's see, 11b minus 25k is equal to 1. Right? And we're looking for integer b for which this is true. Right? In fact, as long as we can find a pair of integers b and k so that this holds, then we're done. Right? Aha, but is this equation familiar to you? Right? We're saying here that 11 times an integer minus 25 times another integer is equal to 1, which is their GCD. This really bezooks identity, which tells us that integers exist for which this equation holds because you have their GCD on the right. And in fact, if you remember how to solve for these integers, you just basically have to apply the Euclidean algorithm, right? And divide 25 by 11. Okay, so I'll do it here. So remember, the Euclidean algorithm is a way for us to compute the GCD of two numbers, right? By pretty much doing repeated division. So first step, you divide 25 by 11, and the division algorithm says, well, 25 is 2 times 11 plus 3. Okay, what's your next step? Next step is you divide 11 by 3. 11 is 3 times 3 plus 2. Next step, you divide 3 and 2. And you get 3 equals 1 times 2 plus 1. And, well, this already tells me, with one more step here, that the GCD is 1. Right? And so, in fact, I can now work backwards here and start with the last equation I ended up with and rewrite it in terms of, well, to have 1 isolated on the right, or I'll do it on the left here, and plugging in a value for 2 based on the second equation. So 2 is equal to 11 minus 3 times 3. And I can simplify this to be 3 minus 1 times 11 plus 3 times 3. Okay, so I'm just going to write that as 4 times 3 here on the left. And finally, let's plug in what we have for 3 from the first equation. 25 minus 2 times 11. And this simplifies to 4 times 25 minus 9 times 11. And that makes sense, right? 100 minus 99 is 1. And what this last equation tells me is this negative 9 number, that will work for B. And it's negative 9 here, it's not 9. Right? So if you multiply 11 by negative 9, you get negative 99, which is congruent to 1. Right? Modulo 25. Well, if you want something positive, you can just add 25 to that. So negative 9 plus 25 to get the next number up in the same congruence class, mod 25, is 16. And this is equal to 176. And 176 is indeed congruent to 1 mod 25. Again, that makes sense, right? Because any number in the congruence class of 16 will work. So we can say that as the following. 16 is an inverse of 11 mod 25. Now, in terms of notation, I can also just say 11 inverse 16. But yeah, that doesn't look as nice, right? So we can also just say this on the right.